This section explains how the real projective plane arises when you take three-dimensional real space and forget everything except direction. A parallel class of lines becomes a point. A parallel class of planes becomes a line. Incidence becomes parallelism, and the resulting structure has no parallels left at all. Any two lines meet. The quotient by direction is the projective plane. Duality arrives free in the same construction. Perpendicularity carries line classes to plane classes and back, an involution that preserves incidence, so the point-line transpose of every theorem is again a theorem. Bamberg and Pentilla go so far as to rename the new objects Pistet and Linjat, blocking Euclidean intuition from leaking in through the words. The chapter's office in the book, projective structure, is Euclidean structure, with the metric quotiented away, and duality is the symmetry that survives. This section explains what a collineation is and why the entire chapter collapses into a single identification of groups. Preserve nothing but collinearity, and you have already preserved everything. Every bijection of the real projective plane taking lines to lines is induced by an invertible matrix, unique up to a scalar factor. That is the chapter's whole content. The automorphism group of the real projective plane is the projective general linear group of the real projective plane is the projective general linear group of the real projective plane is the projective general linear group of degree 3. The consequence is that synthetic incidence questions become spectral ones. A collineation's fixed points are the eigenvectors of its matrix. The 7 classes of fixed point configuration are the 7 ways a real cubic characteristic polynomial can factor, read against eigenspace dimension. The group acts regularly on quadrangles, so coordinates are a free choice of 4 points. No line is the line at infinity until you name it. A conic and an involutive duality are the same datum, one symmetric invertible, 3 by 3 matrix, read twice. Punchley's direction sends a non-degenerate conic to its pole and polar map, which has order 2. Von Stott's direction returns the conic as the absolute point set of any polarity possessing them. Duality. Until here, a symmetry of the axioms becomes a computable map on points. The conic equips the projective plane with its first structure, past incidence, a metric-free orthogonality, where P is conjugate to Q when P times A times Q transpose equals 0. The symmetry of that relation is de Lahire's reciprocity. Theorem 3.13 then collapses the supply. The projective linear group P, G, L of 3 over the reals acts transitively on non-empty, non-degenerate conics, so there is essentially one conic, hence one such structure to exploit. This section explains the cross ratio, the point where the descent of invariance stops. Each geometry is named by what its transformations refuse to destroy. Distance, then equality of distances, then ratio along a line. Under central projection, even that ratio goes, which is why Lorenzetti's tiled floor of 1344 recedes wrongly, as shown in Figure 4 recedes wrongly, as shown in Figure 4.1. The descent stops at cross ratio, a ratio of ratios on 4 collinear points. Theorem 4.7 makes the stopping exact. Quadruples are projectively related precisely when their cross ratios agree. That biconditional upgrades an invariant into a coordinate, the closest thing to length we have in projective geometry, in the words of Chapter 4. Affine ratio comes back by sending one point to infinity, so the weaker geometry sits inside this one as a degeneration. This section explains the group of the conic and why the conic and the projective line turn out to be the same object. A conic is the projective line wearing a plane. The stabilizer of K in PGL3R turns out to be PGL2R, acting sharply 3 transitively on the conic's points. So line and conic are one permutation object, and every invariant of the line transfers intact, cross ratio, harmonic quadruples, separation. Chassel's theorem makes the transfer visible, with the vertex of the pencil dropping out of the cross ratio of the four lines xa1, xa2, xa3, and xa4. The generative move is Frégier's. Every point off K acts as an involution of K, and those involutions alone generate the full group. The plane still pays for itself, supplying what the line cannot carry, an inside and an outside, which the sign of the conic cross ratio reads off. This section explains what an involution is and what the definition is for. An involution is a projectivity of order 2 on a line. Hardy's epigraph to Chapter 6 names its purpose. It does for geometry what the Dedekind cut does for arithmetic. A pair of points that may fail to exist over the reals gets replaced by an operation that always exists, an operation that would have those points as its fixed points. The involution is hyperbolic when two fixed points are real, and elliptic when none are. Over the complex numbers, the distinction collapses into a conjugate pair. Two pairs determine the whole map by corollary 6.3, so the object is finitely given. Abjanker's dictum drives it, adjusts the definitions until the theorem needs no cases. Perpendicularity survives the passage to projective geometry only as this, a relation demoted to an involution on the line at infinity. This section explains one move: delete a line from the real projective plane and affine geometry falls out. That single deletion is the whole chapter. Parallel becomes meets on the line at infinity. Midpoint becomes harmonic, conjugate of the point at infinity, which is theorem 7.1. Affine ratio becomes cross ratio with one slot pinned at infinity. Every affine notion is a projective notion with the line at infinity chosen. So affine theorems inherit projective proofs. Medians concur because Desargues dualizes. Seva and Menelaus are one projective theorem read with the line at infinity as the transversal. Parallel projection is central projection, whose center sits at infinity. The chapter's leverage is that the line at infinity is chosen, not given. A distinguished line is extra structure, and the affine group is just its stabilizer in the projective general linear group of degree 3 over the reals. This section explains how Euclidean geometry sits inside projective geometry as a choice of 2 points. Euclid is projective geometry plus 2 points. Single out the line at infinity, then single out on it the elliptic involution that sends the point with coordinates x, y, 0 to the point with coordinates minus y, x, 0. Perpendicularity is exactly that pairing. Its two fixed points are complex conjugates, I with coordinates 1, the imaginary unit, 0, and j with coordinates 1 minus the imaginary unit, 0. These are the circular points, and they carry every metric notion downstream. A circle is a conic through I and j. Angle is a cross ratio taken against them, which is Laguerre's formula. Foci, axis, and eccentricity all reduce to incidence with that pair. Carathéodory seals it in theorem 8.50. Preserving that involution is what it means to be a similarity. So the chapter earns its metric theorems. The orthocenter draws Farney and Morley from Pappus's involution theorem alone. Measurement adds no axiom alone. This section explains Klein's Erlangen program and what it does to the definition of geometry itself. Geometry is a lattice of groups. Every geometric property is the invariant of some group's action, which means the property has no existence prior to the transformations that preserve it. Klein's move, announced at Erlangen in 1872, runs the definition backwards. Fix the transformation group first, and the propositions of that geometry follow as whatever the group fails to destroy. Ascending the tower is forgetting. Start with the isometry group of the real plane and climb to the group of homeomorphisms of the real projective plane. Distance goes first, then circles, then parallels, then collinearity. Each rung buys a larger group at the cost of a smaller stock of invariants. Descending the tower is imposing. The payload of this chapter is that the descent can be carried out intrinsically from inside the projective setting with no external metric handed in. A polarity on the line at infinity regenerates the Euclidean plane out of the projective blank slate, and the same construction with a different polarity yields Minkowski space. Structure is a choice of stabilizer. This section explains what projective thinking buys you once you learn to run it in reverse. A Euclidean theorem is a projective theorem plus a choice of what to discard, which line to call the line at infinity, and which 2 points on the conic to call I and J. Bamberg and Pentila run that specialization backwards. They lift a metric result to its projective skeleton, then re-specialize along a different choice, and a stranger theorem falls out. 2 circles, tangent, at the point S become 2. Conics meeting harmonically. Send a different line to infinity and parabolas appear. The payoff is equivalence. Who would have seen a connection between Apollonius, Book 3, Proposition 54, and Euclid, Book 3, Proposition 21? Ancient, unrelated, one statement read twice. Symmetry group first. Theorems are its orbits. This part traces how projective geometry emerges once the observer stops standing outside the picture. What remains after that move is the subject of the whole chapter. Renaissance painters did the first half. Brunelleschi's peephole panel fixes a single viewpoint and makes the representation depend on it, so the picture plane cuts the visual pyramid and parallels visibly converge. Des Arges did the second half. He asked what central projection leaves fixed rather than what it changes, and that question forced a line at infinity, so that projection never fails on a special case. Introduce the transformation, then keep only its invariants. That single move is why the chapter can close on Grabener's line before the 17th century geometry studied figures. After it, space. This section explains why projective geometry has a datable birth and what that date actually records. Projective geometry is the one branch with the birth certificate, Poncelet's Traité of 1822, notebooked in a Saratov prison camp after Krasnoy. What that date marks is a change of status. The chapter's thesis is that the same theorems occupy 3 ontological positions in sequence. First, they are scattered results without a home, Apollonius, Pappus, Kepler's point at infinity, Desargues' line at infinity. Then they become a method for doing Euclidean geometry. Then, once non-Euclidean geometry was accepted in the 1870s, they become a method for doing Euclidean geometry. The footnote's counterclaim is where the argument turns. The alleged void between Desargues and 1800 is false. Newton, Maclaurin, and Bézout worked projectively throughout. Results were never absent. What was absent was the frame that would recognize them as one subject. Geometry acquired a plural, and the plural is what made the subject visible. This section explains how Euclidean structure sits inside projective space as a choice rather than a given. Euclidean structure is a choice made inside a planar object. Projective 3, Space over the reals, written PG3R, consists of the 1 and 2-dimensional subspaces of real. 4 space, and it carries no metric at all. Delete a plane pi and affine space appears. Distinguish an empty conic inside pi, and Euclidean space appears. Every metric notion then reads as incidence. Perpendicular lines meet pi in points conjugate with respect to the absolute conic. A sphere is the ellipsoid containing that conic, which is theorem 13.21. The normal to a plane is the pole of that plane's line at infinity. That is the chapter's office in part 2. Install the ambient space, install its group, PGL4R, and install the conic as metric dictionary that later chapters spend rather than justify. This section explains why dimension itself is the proof technique in the chapter on triangles and tetrahedra. Disargys resist direct attack inside the plane. In PG3, over the real numbers, it costs almost nothing. 2 distinct planes meet in a line, and that line already carries the 3 points, P, Q, and R. The planar theorem then drops out by embedding PG2 over the real numbers as the hyperplane x4 equals 0, which is corollary 4 equals 0, which is corollary 14.2. The chapter runs that lift as its single move. The triangle becomes a tetrahedron, and Klein's theorem is Desargues applied to 4 perspective face triangles whose axes glue into one plane. The degenerate case is handled by escaping the plane 2. Build an auxiliary vertex off the plane pi. Apply the easy case there, then project back. The closing bound is the same primitive read backwards. Desmic configurations exist only up to dimension 3. This section explains how 3 skew lines in projective 3 space already carry a surface with them. Take 3 mutually skew lines in PG3 over the real numbers. The set of lines meeting all 3 is called a regulus. The transversals of that regulus form a second regulus, the opposite one, and together the 2 families rule the hyperbolic quadric, whose equation is xw equals yz. Nothing else rules it, and the quadric determined by 3 skew lines is xw equals yz. That identification is the chapter's whole move. A line theoretic object, the transversal closure of a triple, and a quadratic form object, the 0 set of a symmetric matrix, turn out to be the same thing. Once they coincide, incidence facts convert into algebra, and algebra converts back into algebra, and algebra converts back into algebra. The closure comes from the Dandelin and Gallucci theorem, 15 of 16 incidences, force the 16th. Schläfli's double 6 and a second proof of Pascal's theorem then fall out as corollaries. Elliptic quadrics carry no lines at all, same form, wrong signature. This section explains what happens when you change which object counts as the primitive element of a projective space. Change what counts as a point, and the dimension count changes with it. Plucker's move is to take the line as the primitive element of projective 3. Space over the reals. The totality of lines is then a 4-dimensional object, coordinatized by 6 numbers, 1, 2 by 2 minor per index pair of the 4 homogeneous coordinates, subject to 1 quadratic constraint. 1 quadratic constraint L1 times L6 plus L2 times L5 plus L3 times L4. What the chapter buys is theorem 16.8. The synthetic recursion defining lines, linearly dependent on others, pencils from 2 coplanar lines, reguli from 3 skew ones, coincides exactly with linear dependence of their Plucker vectors. Geometry of line families becomes subspace dimension. Congruences sit at 4 independent lines, complexes at 5. The proofs wait for the Klein correspondence in chapter 20. This section explains what perspective is once geometry stops privileging any single plane. Perspective is what geometry looks like once you stop privileging one hyperplane rather than a distortion added on top of it. A central projection through a point P from a plane P to a plane P prime is the isomorphism of projective planes. Compositions of such projective planes, compositions of such projections taken back onto pi generate the full projective general linear group of degree 3 over the real linear group of degree 3 over the real numbers. That generation is the step that does the work. Poncelet, in 1822, defined projective geometry as what survives projection. Klein's Erlangen program defined it by group invariance. The two definitions collapse into one another, a single object seen twice. Vanishing points then need no optics at all. They are images of points at infinity. The horizon is where the plane through P, parallel to the scene, cuts the picture. The chapter's payoff, a pinhole camera, is a singular linear map. That singularity is why homogeneous coordinates make vision computations linear. This section explains what the Euclidean plane becomes when you add a single point to it. Add one point to the Euclidean plane, and lines stop being a separate species from circles. Both become the same object, and the geometry that results is the one where inversion in a circle is a global symmetry rather than a map with a hole at the center. 3 points then determine a unique circle, exactly as the line at infinity made any two lines meet. The chapter's payload is that this inversive plane is the complex projective line, PG1, over the complex numbers, with its real sublines as circles. So a Euclidean statement about circles becomes a statement about a cross ratio being real, and Meckel's six-circle theorem falls out of a projective fact already proved. Circles were never extra structure. They were the real points hiding inside a complex line. This session explains how projective geometry moves up in dimension, and where that move stops being free. Projective space, written Pg of D and R, is the subspace lattice of R to the D+1, and every interval inside that lattice is again a projective space of the same kind. So the entire apparatus built for the plane and for 3 space lifts with no new argument, only relabeled dimensions, Grassmann's identity, frames duality, the group PGL, de Sargas, no new arguments, duality, the group PGL. The chapter's real work begins where lifting stops being free, where dimension buys room. Segre's 5 associated lines live only in PG of 4 and R. Baker's remark carries the compression. 3 lines in 4 dimensions have just one transversal. Schleffli's double 6 in 3 space then falls out by embedding the configuration in PG of 4 and R and projecting it back from an external point. Ascending in dimension is a proof technique aimed downward. What genuinely resists the lift is quadratic classification. There, Sylvester's pair of rank and signature replaces the plane's single equivalence class. This section explains one move, raise the dimension, and the object becomes a point. A line of projective, 3 space over the reals written PG3R carries 6 Plucker coordinates, so the entire line geometry of 3 space sits as the Klein quadric inside PG5R. A conic of projective 2 space PG2R, a conic of projective 2 space PG2R carries 6 coefficients, so the family of all conics sits as the Veronese surface in that same PG5R. The gain is that relations degrade into linear algebra. 2 lines meet exactly when a bilinear form vanishes, and classifying congruences and complexes becomes the question of how a subspace can cut a quadric. Mackenzie's shirt crammed into a 2-full suitcase, the chapter 20 epigraph, extra dimensions, smooth the pinch points. the recipe reaches any family whose members already carry a coordinate vector.